High above Earth's horizon, the moon has always watched silently, cold, ancient, and still. For millennia, it has been the symbol of constancy, a lifeless mirror reflecting our blue planet's brilliance in the night sky. But what if we've misunderstood it? What if the moon is not a relic of stillness, but a world in flux? In 2020, planetary scientists uncovered a shocking truth. On the moon, a place without air, rain, or liquid water, something impossible was happening. Rust. Yes, iron oxide. The same substance that turns Earth's bridges red and Mars's surface orange was forming on our own moon. The discovery shook assumptions across planetary science. Rust needs oxygen. It needs water. It needs weather, none of which should exist on the moon. And yet, there it was, coating crater rims, staining ridges, whispering a story written in chemistry. A story not just about the moon, but about Earth's influence, the delicate forces of space, and how even in silence, celestial bodies interact in ways we're only beginning to understand. This isn't just a mystery. It's a redefinition of what the moon is. For decades, our understanding of the moon was simple: airless, lifeless, bone dry. When Apollo astronauts first brought lunar samples back to Earth, the rocks appeared devoid of moisture, vacuum-sealed by the solar wind, scorched by UV radiation. The moon was considered a sterile desert of silicate dust and craters. This belief shaped mission planning for decades. Colonies would need to bring their own water. Mining or chemistry-based resource generation wasn't feasible. But all of that began to change in the 2000s. NASA's Lacrosse mission deliberately crashed a probe into the moon's south pole, and in the plume, instruments detected unmistakable signs of water ice. Not just traces, deposits. Then came India's Chandrayaan-1, which mapped hydroxyl molecules across the lunar surface, even in sunlit regions. The moon, it seemed, was not dry after all. It was chemically hydrated. Still, the water was thought to exist in frozen form, in shadows or deep underground. Until, in 2020, data analysis revealed something far stranger. Scientists weren't just finding water. They were finding hematite, rust. And that changed everything. To understand why rust on the moon is such a shock, we need to understand the chemistry. Rust is iron oxide. It forms when iron reacts with both oxygen and water, especially in the presence of moisture and time. It's the process that turns steel red, corrodes tools, and transforms Mars into the red planet. But none of those ingredients, not liquid water, not free oxygen, exist naturally on the moon. So how did hematite form? Initial analysis revealed that the hematite was most abundant at higher lunar latitudes, near the poles, particularly on the Earth-facing side of the moon. That geographic bias offered the first clue. Something from Earth was involved. The breakthrough came from a deeper look into the moon's monthly orbital path. For several days each month, the moon passes through Earth's magnetotail, the extended portion of our planet's magnetic field that trails away from the sun like a comet's tail. When this happens, two things occur simultaneously. Solar wind is blocked, meaning fewer hydrogen atoms bombard the moon. This matters because hydrogen prevents oxidation by bonding with available oxygen. Oxygen from Earth's upper atmosphere escapes into space and drifts along the magnetic field lines straight toward the moon. For billions of years, this trickle of oxygen may have bathed the lunar surface, providing, in just the right regions and in just the right moments, the key ingredient for rust to form. Not in great rivers, not in floods, but in slow, molecular whispers. Rust needs more than oxygen. It also needs water. And while the moon has no rain, oceans, or humidity. Scientists now believe it has more water than we ever imagined. Where does it come from? One source is solar wind, streams of charged hydrogen particles from the sun that strike the lunar surface, where they react with oxygen and lunar minerals to form hydroxyls, OH, and H2O. Over time, this water becomes embedded in the top layer of lunar soil. Another contributor is meteoritic delivery. Micrometeorites, constantly striking the moon, contain trace amounts of water locked inside. When they impact, that water is released. Some of it may remain trapped in the regolith. Some may escape, but in certain conditions, it could bond with nearby iron and oxygen, sparking slow oxidation. And deep in permanently shadowed craters, there is actual frozen water ice, preserved from the time of the moon's formation or deposited by ancient comets. So while the moon doesn't have oceans, it has enough water, in enough forms, to support rust, at least in trace amounts. This challenges our definition of what water-rich really means. Perhaps the most compelling evidence of Earth's role in lunar rust lies in its asymmetry. Rust isn't evenly distributed. It's heavily concentrated on the side of the moon that always faces Earth. Why? Because the magnetotail and the oxygen ions it carries is channeled almost exclusively toward that hemisphere. The far side of the moon, shielded from these Earth-based inputs, has significantly less hematite. This suggests that the moon is not merely a passive satellite. It is actively shaped by Earth's presence. Our planet, through its atmosphere and magnetic field, is subtly modifying the surface chemistry of its nearest neighbor. That's a profound realization. It means that planetary interactions extend beyond tides and gravity. They can alter surface chemistry, even geology. The rusting of the moon isn't just a lunar oddity. It could change how we view planetary bodies across the solar system. If Earth can affect the moon's chemistry over distance, what else is happening unseen? Could Mars's widespread rust have been amplified by similar processes in the early solar system? Do other moons, like Europa or Ganymede, receive atmospheric particles from Jupiter, influencing their ice and mineral structures? Could asteroids near Earth pick up trace atmospheric elements as they pass through our magnetosphere? And finally, could we use lunar hematite as a timeline, a record of how Earth's atmosphere has changed over billions of years, preserved in rust? Each possibility opens a new frontier in planetary science. The timing couldn't be better. NASA's Artemis missions are preparing to return humans to the moon, not just for a visit, but to build a permanent presence. Knowing where water exists and how it chemically behaves is critical. Hematite deposits might help identify regions rich in water-bearing minerals. Understanding rust formation could help design materials and habitats to withstand long-term lunar exposure. Future missions may carry spectrometers to scan for hematite in real time or dig beneath rusted layers to uncover water sources. Even robotic rovers, like those planned for the Viper mission, could explore polar regions to map oxidation, water ice, and mineral chemistry. We're no longer just visiting the moon. We're about to live there. And with every new discovery, even something as simple as rust, we're learning how to survive and thrive in space. In the end, rust on the moon is more than a curiosity. It's a symbol, a sign that even in the coldest, driest places, the universe is in motion. That worlds are not isolated, but connected chemically and magnetically in ways that take eons to reveal. The moon, once thought silent and inert, is quietly telling a story written in iron, colored by Earth, sparked by sunlight, whispered in dust. We used to look up at the moon and see only mystery. Now, We look again, and we see chemistry, history, and connection. The moon is rusting, and in that rust, we find a bridge between Earth and space, between what we thought we knew and what we're just beginning to learn.